Well, I think maybe it's time to get started. So welcome to today's webinar, which is part of the Young Scholar webinar series on climate change, macroeconomics and finance, organized by the E-Axis Forum. I'm Connor Walsh. I'll be the moderator for today. And today we have Jeffrey Sun, who will present his paper, The Distributional Consequences of Climate Change, Housing Wealth, Expectations and Uncertainty. Jeffrey Sun is an assistant professor in the Department of Economics at the University of Toronto. He graduated with a PhD in economics from Princeton University in 2024. He's interested in combining climate science and structural economic modeling to study the equilibrium impacts of climate-driven environmental changes. He also develops computational tools for solving rich heterogeneous agent models. So Jeffrey, take 45 to 50 minutes for your talk, and then we'll have a Q&A. I'll leave time for questions after the presentation, and to ask questions, please use the Q&A function at the bottom of the screen. Enjoy the talk.
All right. Thank you so much, Connor. And thank you, Anastasia, and to the E-Axis Forum and everybody there for this amazing opportunity. So today I'm very happy to be talking about my paper, The Distributional Consequences of Climate Change, Housing Wealth Expectations and Uncertainty. So the motivating impetus behind this paper is that we expect areas that are going to be impacted by climate change to experience not only a direct impact to the quality of life of people who would be stuck in that location, but also reduced population as people move away and reduced house prices. Now, I mentioned house prices, which might seem like a technical detail here, because in the US, for the median household, the amount of wealth that they have in their home is greater than the amount of wealth that they have in all other assets combined, right? The majority of the median household's wealth is just in their home. And so those fluctuations in house prices are expected to be highly redistributive across a lot of margins. In particular, this is something that is not covered, is not incorporated as a model feature in a lot of the typical migration models or climate response models that we see. So what I'm going to be doing in this paper is a model-based approach, right? And this model is going to first essentially take in some data about climate impacts and then provide some machinery to interpret what those impacts might be along various margins. So we're going to start off by developing a strategy for taking existing estimates of climate impacts at different levels from different parts of the climate economics and climate science literatures, in particular on the impact of climate change on quality of life through changes in heat, impact on labor productivity through changes in heat, and on disaster damages through changes in flooding propensities. And we're going to plug these into a model, which is going to give us the ability to interpret and predict, forecast the impacts of these on endogenous house prices and rents, and then quantify what the wealth and welfare impacts of those physical climate changes and housing wealth changes are going to be along margins such as space and economic margins such as wealth, income, and housing. To put this sort of crisply, we want to understand who wins and who loses from these house price changes, right? What are the differential impacts based on whether somebody is living in a more exposed or a less exposed location, and whether somebody owns a home or rents. And in addition to this, looking a bit forward into what this research program might enable us to do, we also want to look at, in future work, how this impacts institutional landlords, such as these private equity firms that are increasingly buying up family properties, residential real estate properties, and how people who are better informed and people who are worse informed are going to be potentially differentially impacted based on their ability to correctly assess the value of real estate assets. I'm also going to be looking at a couple potential policy implications of this. The one that I'll be highlighting in this presentation is uh, a sort of basket of policies which we can group together as those intended to make migration easier. That is, you can imagine policies which, without having direct economic impacts, might help people move out of more flooding exposed locations by helping them match with employers in less exposed locations, helping them find landlords, and sort of easing the moving process. And what we're going to see is relative to the existing climate impact migration literature, that consistent with that previous literature, easing migration is going to reduce the spatial inequality in physical, what I'll call the physical impacts of climate change, because people in more negatively exposed areas, if they can move out more easily, they're going to be less exposed to the durable welfare impacts of a changed environment in that location that they would otherwise be more stuck in. However, in contrast to the existing literature, this is also going to increase spatial inequality along it through one channel, which is the housing wealth impacts. That is, with easier migration and larger population outflows from more negatively affected areas, we find in the model that housing prices fall faster in these negatively exposed areas, and that's going to increase both spatial inequality in that housing wealth channel, as well as being severe enough that some households, particularly those who are older and those who have a higher share of their wealth through housing, will actually prefer that the migration policy not occur. That is, this migration policy, which is seemingly innocuous, can actually be negative for some households and create losers as well as winners. So the literature that I think this fits sort of most closely into would be this fairly recent so-called dynamic spatial climate assessment literature. And this is a literature which starts out with a fairly simple premise economically, which is that starting with an equilibrium, we want to plug in some climate-related shocks into that equilibrium and understand what the welfare impacts of that are going to be when agents in the model have some means of adapting to it. We can look at, for example, the classic paper of Desmond and co-authors 2021, in which there's just some exogenous loss of land area due to coastal flooding, but in which agents can reallocate capital across space and reallocate labor across space, that is migrate, all the way to, on the more complex end, the paper of Bilal and Rolsey Hansberg 2023, in which climate change impacts both local amenities in a spatial varying way, labor productivity, and the rate of capital depreciation, but people can adapt both through those aforementioned capital and labor reallocation channels, as well as adapting in a forward-looking way. That is the future anticipation. So this is a literature in which we're taking this fairly simple economic proposition and studying them in a model with high-dimensional space. The constraint that this literature hits up against a lot is computability. Each of the following four enrichments, heterogeneity, frictions, anticipation, and uncertainty, add an exponentially higher amount of computing load to solving a model of this form. So part of what's going along with this paper is a lot of work in the solving of high-dimensional models that's going to make the model I'll describe actually feasible to solve and kind of push this literature forward in terms of complexity. Okay, so what does this model look like? Well, let me take a step back here and say that the way I'm going to be presenting this model is almost in the spirit of the agent-based modeling literature, except that we're actually going to be embedding this in, a completely rigorous sort of standard macroeconomic model. And what I mean by that is that we're first just going to be defining the problem of the agent, which is going to be fairly complicated, and then embed these agents into a high-dimensional spatial environment in which prices are going to be endogenized just through the interaction of these agents. Okay, so zooming in on a single agent in a certain place, they're going to make a budgetary decision and a migration decision. What that budgetary decision looks like is that they are going to have in each period, time is finite, time is discrete, a budget which is made up of the following four sources. A value of their financial portfolio consisting of both the liquid asset and potentially real estate, their labor earnings from that period, their rental income that they might receive from properties that they own and rent out to other households, and their interest income on their liquid savings. Having this budget that is so constructed, they are then going to decide how to allocate that budget into four different buckets. Their consumption in the present period, their saving in the form of a liquid asset, their saving in the form of purchasing residential real estate to then live in, and they're saving in the form of purchasing residential real estate to then rent out to other households in the same location for interest income. They're going to do this in a forward-looking way, subject to a set of frictions and uncertainty about future climate impacts in order to maximize in a standard way their net present value of expected lifetime utility. In addition to this budgetary sort of slightly complicated consumption savings decision, they're also going to make a migration decision. That is that in each period, they start off as a state variable, with a location as a state variable in one location in space, and then choose their location for the following period, following the realization of a full set of standard extreme value type 1 location preference shocks, which is essentially going to make their migration decision constant elasticity substitution across locations, with a higher weight on locations that are closer to them, calibrated to match migration flows in the data. Households live between the ages of 20 and 80 in periods of 10 years, and they enter with heterogeneous liquid wealth and income and distributed across space somehow. Now, in a model in which we have these agents endogenizing local housing prices and local rental rates, we are also going to hit the model with a certain climate shock. And what that climate shock looks like is that there's going to be sort of a single summary statistic for the state of the global climate, which is the global sea surface temperature. Then in each location, there are going to be completely flexible local sensitivities to that global sea surface temperature, right? So in an area that is, for example, extremely cold, which might in a local sense improve in response to a change in global temperatures, there will be a certain sensitivity, a certain value of that sensitivity in which the derivative of the local quality of life or location amenity with respect to the global sea surface temperature might be positive. In an area that is already hot and does not benefit from getting even hotter, this derivative might be negative. And in particular, I'm going to log linearize this in the following way. So for the labor productivity shifter, for example, in each location, the log of that variable is just going to be equal to some sort of baseline value plus GIA, where I is the location, a location-specific sensitivity to the global climate state. And the same thing is going to be true of the local location amenity or quality of life shifter, shifter indicating controlling how desirable a location is for non-wage reasons. non-pecuniary reasons, and disaster damages in each location, which are going to capture the probability and expected damages from floods. So having written down this somewhat complicated model, we're going to need to somehow put numbers to it. And there are two sort of sets of variables that are going to come out of here. First, what I'll call the baseline parameters, which are the parameters which are totally unrelated to climate, which control the steady state equilibrium of the model, which we're going to calibrate to match data from the United States in about 1990, in particular the 1990 US Census, 5% subsample, and the 1992 Survey of Consumer Finances. Having calibrated the model to look both in aggregate and spatially like the US in 1990, we then need to put numbers to the climate sensitivities. And the way that this is going to work is that, as stated before, we're going to need to introduce a variable such that controlling the local flexible climate sensitivities of labor productivity, disaster damages, and the quality of life shifter for each location. The challenge here is that these are not cleanly readable off of the data. And in fact, they're not even cleanly readable off of any existing studies. So what we're going to try and do is try and find impact estimates from the literature, which are simultaneously compatible with the model. That is, they are attempting to measure the same thing that we are plugging into the model as a parameter, that they are mutually consistent with each other in identification, by which I mean that they are avoiding double counting problems. So for example, if you have a model which is, if you have an empirical paper which is trying to measure the quality of life in a certain area, if that measure of quality of life is picking up the impact of floods on people's desire to live in a certain place, then it would be double counting in a sense to increase this quality of life shifter taken from the literature and the flooding shifter, because then the data on floods will be mapped both to the data of floods in the model, which affect people directly, and implicitly through the quality of life impact of floods. So they're going to need to be mutually consistent identification, as well as applicable to different locations, years, and scenarios. We ideally want to be able to plug in, a certain scenario without having to completely re-estimate the entire model. We don't want to do something that is really tailored to a certain socioeconomic pathway or a certain RCP. And what we're going to do is exploit the following two facts. And this is sort of a novel strategy. First, the fact that we have climate models which translate global sea surface temperature to local temperature measures, in particular, heating degree days and cooling degree days, in a way that is approximately linear. And second, that we have estimates from the environmental economics literature of impacts of heat on quality of life, or impacts of local temperature conditions on quality of life and labor productivity, which, even when estimated in a more when I say more parameterized way, a more flexible way, still appear to come out almost log linearly in exactly these local temperature measures. So by linearizing through local heating degree days and cooling degree days, I posit that we have a strategy for estimating exactly that sensitivity at the location level of the response of labor productivity and the location amenity with respect to global sea surface temperatures. Okay, so having put all of these numbers into the model, I want to talk a little bit about exactly what we find. And the experiment that I want to put in here, I apologize for the construction, is that we're going to start out in a baseline, which is calibrated to 1990, and that's going to be treated as a stationary steady state. It's 1990. It's always been 1990. Everybody expects that 1990 will continue forever. And then at a certain year, which I'll denote 0, the news is received that the globe is going to heat up by 1/10 of a degree 10 years in the future. And sort of the point that I want to make here is that at this time 0, nothing physically changes, right? As far as you could tell empirically from the physical variables in the model, that news could be mistaken. But because housing prices and household saving and migration decisions are highly forward-looking objects, this is going to cause an immediate impact on the equilibrium distribution of populations and the equilibrium housing prices. So we really want to understand the effect of this news. On the other hand, in order to really understand the effect of this news in a proper rational expectations framework, we need to solve for the whole equilibrium following the receipt of the news into the future. So the first thing we can look at is just the spatial margin of heterogeneous impacts. In particular, what I'm going to show here is the impact of that news on people's expectations of their future lifetime consumption. That is, how much did they think they would be able to consume in expectation for the rest of their lives before the news received? And how much do they now think that they will be able to consume over the course of their lives? And we can see essentially, I want to draw your attention to basically 2 margins of variation that are shaping this map. One of them is exposure to coastal flooding, right? We have these highly flooding exposed areas on the East Coast, and that's causing the most severely impacted individual areas to be along the coast here. However, the majority of the impacts overall are going to be driven by what comes up here as largely a north-south gradient, which is going to be changes in heat. Areas that are already hot and projected to get hotter are going to be getting worse. Areas which are already cold and are projected to get less cold are going to be getting better. Now, the locations that I'm using here, you might notice that they're not exactly lined up with counties. These are public use microdata areas. And one very nice thing, which I didn't plan about public use microdata areas, is that they're a population-based location definition. I think there are areas with between 100,000 and 200,000 people in 1990, but I could be wrong about that. And because populations are more concentrated along the coasts, it gives us higher definitions, locations, exactly where we want them, exactly where those flooding impacts are going to be the most spatially dispersed. So zooming in on Florida, you can kind of see the resolution that we're talking about. This area right here is going to be slightly more is going to be substantially more impacted than the area right next to it. And looking down at Miami, we can see that there's a very negatively affected area surrounded by less negatively affected areas, which is sort of tracing out the outline of the Everglades. If we want to look at now what the immediate equilibrium response is going to look like, that is the response to the news, we can plot these out, and they look broadly the same. Prices drop exactly in these negatively affected areas and rise in the most positively affected areas. These are house prices. And populations follow about the same pattern. People move out of areas that are going to get worse and into areas that are going to get better. So given this, we might want to ask, can we compare the impact of those housing wealth changes to the impacts of the overall climate changes? And so what I have here is a first plot, which is exactly what you saw 2 slides ago, what the overall expected change in lifetime consumption is going to be. And I want you to read these 3 maps like this. This equals this plus this. So the overall change is the sum of the welfare impacts of this housing wealth change and everything else. And I want to say at this point that I'm not playing games with you. I know that the 3 color scales on the bottom are not the same, but if they sort of were calibrated the same way, it'd be very hard to see the variation here. In fact, we have just over 10% of the overall welfare impacts coming from just the housing wealth impact. But this is a sort of 10% of the spatial inequality in climate change that we would not be able to see without performing this exercise. So let's zoom in on that second map, the component that's due to the housing wealth impact. So zooming in on a few slices of this model in order to really see some numbers. First, we're going to condition on this puma right here, this location, which is the area close to Florida that is primarily the Everglades swamp. We're also going to condition on households in the median income group and households who don't own any investment real estate. Then if we put the overall wealth on the x-axis here and the housing wealth on the y-axis here, we see the results of what is essentially a sanity check that turns out the way we want, which is that households that are wealthier experience a lower impact than households that are less wealthy, conditioning on housing wealth, and conditioning on a level of wealth, wealthier households who have a greater share of their wealth in their house are more negatively affected. Finally, we compare this age 40 group with this age 60 group. We see that the older households are more negatively affected as a result of the fact that they have a greater share of their future consumption out of their housing wealth as opposed to out of income. Okay. Now, to look at that decomposition that we looked at in the form of maps, in the form of economic margins. So conditioning now on that same Everglades puma we were looking at before, the median wealth group, the median income group, and households with no investment real estate, I plot 3 of these kind of welfare along economic margins, and they're read the same way. This equals this plus this. So on the x-axis here, I've changed it up a little bit. We're conditioning on median wealth, and then on the x-axis, we just have housing wealth. And then on the y-axis, we have age. So if we look at the overall welfare impact, we can see that younger households are more negatively affected, older households are less negatively affected. And this is true not just because of the exposure to housing wealth, but because these younger households are more exposed to future periods in which the climate change is actually realized, and older households still are enjoying a full period without the actual physical changes. But as we see, if we get to the final column here, where households are very rich in housing wealth, then the impact along the age margin starts to look a little bit more nonlinear, non-monotonic. So if we do that exercise we did before, where we decompose that overall welfare impact into the housing wealth channel and everything else, we can see that that non-monotonic impact along the age margin for these housing-rich households decomposes into two monotonic components. In the housing wealth channel, it's simply the case that households that are richer in housing wealth are more negatively affected, and households that are older are more negatively affected when after conditioning on the level of housing wealth. And in the third panel, we can see that that eats up basically all the variation along housing wealth. So there doesn't appear to be, at least in this model, another channel by which households are really differentially affected by their housing wealth. You might imagine, that different levels of housing wealth might affect households' consumption baskets, households' mobility. This is not a channel that's going to come out of this model. So we have quite a clean decomposition into physical impacts or non-housing wealth impacts that are basically purely a function of age, and this housing wealth channel, which is somewhat a function of age and then quite visibly a function of housing wealth. Now, it doesn't do us a huge amount of good to just be able to say that some households are negatively affected without any discussion of what we can do to help them. So what I'm going to do in my final exercise here is one example of a lot of different policy experiments we could run on this model, which is to look at a version of the model without migration, right? So I'm sort of going at this question about whether a policy to make households, to make it easier for households to move. I'm sort of going at that policy question a little bit backwards. I'm saying, what if we went back the other way, just to make a cleaner exercise here. So in a version of this model without migration, the populations in the baseline are going to be held to what they are in the model with migration. But we're going to compare a future in which households are not allowed to move, but there's no climate news or impact, with a version of the model in which households are similarly not allowed to move, but that climate news is received. And what we see is that the price responses in the model without migration, which is the new one on the right, are quite muted compared to the house price changes in the model with migration, which you already saw, which I put on the left. In fact, house price responses are about 48% smaller on average, and that's really just going to be picking up the change in labor productivity and not the change in the demand response through out-migration. To switch now from the spatial margins to the economic margins, we go back to the same condition we were doing before. In that Everglades location, conditioning on the median wealth group and the median income group and households with no investment real estate, I compare the impact of that news on households in the top row with migration. So this is what you already saw, but I've added a second row representing the measurements that come out of the model without migration. And just eyeballing it, you can see that on average, this version without migration is going to be worse for most of these groups, right? Now, not only are you in the Everglades, when you learn that the Everglades is going to be a worse place to live in the future, in addition to that, you're also stuck there, right? So these young households are sort of substantially worse off not being able to move out of the Everglades. But in this top right quadrant, we see that there are households who are actually better off in the model without migration than in the model with migration. So one suspicion you might have about where this is coming from is that households who are older and more housing rich because they're so exposed to house price changes, and house prices are not dropping as much in the Everglades because demand is being supported by all these people who are stuck there, they're going to be worse off. They're going to be better off if everybody is stuck there supporting their house price. And indeed, when we do that decomposition, we see that that's exactly what seems to be driving it. In the housing wealth channel, pretty much everybody is less affected through the housing wealth channel in the version without migration than in the version with migration. But this really starts to bite with these older housing rich households or highly housing exposed households. But uh, once we take that out and look at the so-called physical impacts, the physical impacts are pretty much roundly worse for everybody in the version without migration. And in fact, I took this slide out for time, but when we start looking at households who have a certain amount of investment real estate, these trends become even more dramatic. Households that have a large amount of investment real estate are going to be even more negatively impacted through the housing wealth channel. Okay, so I'm a little bit early on time, but I think that just gives me more room for questions. I'll just recap a little bit what the exercise is and where we hope to go with it. The whole kind of goal here is to just understand, with a complicated answer, a simple question, how is climate news and uncertainty going to affect housing wealth? And how are the gains and losses of housing wealth changes going to be distributed? To put some numbers to it, the news of that climate change onset that I talked about explicitly is going to cause an immediate reallocation of wealth of about $41 billion just in response to the news. And in some sense, you can think of this as a result about the role of information, right? We could imagine this as an exercise about the warming as something that it's going to occur at some point, certainly. And then the model becomes a little bit more about the role of informing the population that this impact is going to take place. There's another experiment that I didn't include here, which is comparing a sort of perfect foresight climate transition to a climate transition in which there's ongoing uncertainty on the part of households. And what we find there is that the uncertainty in some sense gets priced into the real estate prices, which makes future young prospective homeowners and sort of the rich cohorts being born not much worse off because, again, they now have cheaper access to investment real estate and home-owned homes. But it does reduce the supply of new residential real estate by reducing the prices, which is going to essentially be passed on to renters in the form of higher rents. And this ends up being a pretty strong regressive impact along the wealth margin. Renters tend to be poorer, homeowners tend to be richer. And so this is going to represent, if we look at the cohort that's born in 2050, approximately a $94 billion wealth transfer equivalent from the poorer half of the population to the richer half. And then pulling back a little bit and thinking more generally, a lot of the impetus behind this project is that there are just a lot of concerns, a lot of questions we have about the impacts of climate change, which are highly spatial in nature and which really involve us trying to figure out who the winners and losers of certain changes are going to be, what the inequality and heterogeneity in those impacts are going to be, and how these things are going to be shaped by certain frictions and people's inability to adjust up to the first best. So there's a lot of work that went into this in terms of just sort of general tools for which this is an example or an application. um, that combine space, heterogeneity, serious frictions, and expectations and uncertainty, which can be used to study all kinds of shocks, of which climate shocks are the ones I'm interested in. And with that, I'll wrap up the presentation part. Connor?
Great, thanks, Jeffrey. That was really fascinating. I mean, maybe I'll just start there. On the technical aspect, I guess for people who aren't familiar with these models, incorporating uncertainty into high dimensional space is often quite a bit of a challenge. And as I'm looking at it, I'm thinking, kind of, how did you solve this? Because usually the fear with these kind of models is that you'll have to keep track of distributions and forecast them forward.
Yeah.
And you didn't say much about the solution of the model. So why don't you start with just telling us a little bit about how you develop some tools to come get around these challenges?
Absolutely. Let me see if I have a little visual aid here. Here's all the gnarly math behind the actual model itself.
Fantastic.
Um, and then let's see. This is a pretty core part of the main presentation. Well, I can say this. Yeah, let me do this verbally. So it's really a combination of a lot of conventional methods, just really broken down and optimized and thought about very carefully. And specifically, just to introduce uncertainty, a little bit of the application of a neural network. So in terms of the model without uncertainty, it's just a sort of painstaking process of breaking down each of the agent's decisions and each of these state transitions into little kind of sub-stages, and thinking of a single period in the model as being really a sequence of like 20 different stages in which one thing happens, one thing happens, one thing happens, and then just me sitting in my room for months optimizing each one of these to make it go as quickly as possible. The introduction of uncertainty typically is associated with what's called the curse of dimensionality, that we'd have to keep track of sort of the future distribution of possible population distributions, which is an immense object. In order to get around this, uh, I introduce a neural network purely to predict for each household what the continuation value would be of ending the period in a certain state. So if we think about kind of a function, um, which takes in the current climate state, the current distribution, and a end of period state for an agent, we would like that to be able to spit out what is the value of being in that state, right? 2 points. The first is that if we had such a function, then households could just look at the conditional continuation values of every decision they could make each period. That gives them essentially like a terminal payoff for their problem, which they can just iterate backwards in a standard way. The second is that that kind of evaluation of different states is something that neural networks are very good at, right? Um, to go a little bit, I'll make one last note, which is that a lot of the sort of using neural network to solve macro models literature uses neural networks to parameterize the policy function of the agents. And, this is something that I actually tried to do for about a year before deciding that for something this complicated, it was just really, really hard to train, really finicky, and unnecessary. All you need is to know what those conditional continuation values are going to be,
Mhm.
and then conventional methods carry you the rest of the way in a much more transparent, flexible way. So,
Really interesting stuff.
yeah.
That's
And
great.
the companion paper there is called Continuation Value is All You Need.
Great title. Okay, I might ask Thea Kalasa to unmute herself. She has a couple of questions if she's there. Otherwise, I can ask them for her.
Yes, I'm here. Thank
Great.
you. Super cool project. Thank you so much for the presentation. I was wondering two things, and maybe I'll just start with the first one and then the other one. They are not related. So my first question was on that governments often intervene in housing markets through disaster aid, through insurance subsidies, or adaptation measures. How do you think incorporating different kind of policy measures would affect the welfare? And what do you think about the which policy response do you deem to be most effective in this way?
Excellent question. Uh, sorry for the pause. So there are definitely things I can say and things that I can't, right? Um, there was sort of an early stage at which it seemed very natural to be talking about looking at an flood insurance subsidy in the light of this, in the context of this model. I think that's still going to be something that I'm going to try and put in by, the real submission. But there's a real barrier there, which is just that uh, endogenizing the insurance rate in such a way that it's consistent with data has been tricky. Insurance rates really reflect something about, again, expectations over, what future realizations are going to be and the risk appetite of the insurer. They depend on a lot of proprietary data, which is hard to get your hands on. Um, but in principle, a simple version of this is very easy to plug in, right? We imagine that households are just not suffering the full impact of these disasters that occur. Um, and just mechanically, what's going to happen is that uh, this is going to make these climate affected areas more expensive. Sorry, more expensive to the government and more highly populated by households who are not internalizing those costs. In some sense, I would say the contribution here is just in providing a way of plugging in data about migration in such a way that we can understand how these economic factors interact with people's migration, like what the migration elasticity to the effective income represented by the insurance subsidy would be. In terms of effectiveness, I would say that there's a little bit less that I can say about comparing a broader class of policies, because there's not that much room within the model for either adaptation or mitigation, for the effectiveness of adaptation or mitigation, right? All adaptation is pretty much going to enter the same, right? It just lowers the impact of the climate change on a given location. So you would need to provide as an input here how effective it's going to be in reducing the quality of life and so forth. And with mitigation is the same. You would have to plug in as an input to the model what the counterfactual changes in temperature are going to be.
Super interesting. Thanks.
Thanks for
Now the second question that I had was that house prices in your model and rents, they seem to adjust immediately to new climate information. And in reality, house price dynamics are more gradual and subject to a lot of frictions. Now, if house prices and rents, they are adjusting slower, how would you think this shapes the distributional impacts of your model?
So there's an interesting empirical question here, which is how quickly do house prices respond to information, right? There are two sources of lags. There's the fact that people's beliefs change at a lag to the information coming from climate scientists, and there's potentially house prices reacting at a lag to people's beliefs. What I'm plugging into the model in the example shown here is that people's beliefs actually change all at once, right? Given this sort of sudden change in people's beliefs, I think, indefensibly, I guess, but that the sudden response of prices is fairly reasonable. The question then just becomes how gradually do people's beliefs change, which is something I'm looking at. And I think to address your question about how this would affect things differently, one exercise that I'm currently working on is sort of a version of this in which some households, say information is released, some households believe it, some households don't, right?
Mhm.
And then the exercise is just these households who believe that the climate is going to change. Let's assume that they're right. Climate change is real. They have superior information, and so they're going to be able to make certain trades that are better informed than households who don't believe it, right? And so that kind of role of heterogeneous information is something that, let's say, I'll have a much better answer for you in a couple of weeks.
Cool. Thank you so much. Looking forward to it.
Thanks.
Great stuff. And I mean, in the same vein, we've got a question in the Q&A. Alice Hoare is asking you to speculate a little bit, I guess, given your work in this area. I mean, she said, when do you think these climate risks will start to materially impact house prices? For example, Florida is very exposed to climate impacts, yet house prices continue to rise and investment continues to flow into real estate in Florida due to tax breaks. It seems that the problem is still too far away to be material in the real estate market. I must admit, I've wondered the same thing about, Florida's going to, or Miami's going to be underwater in 10 to 15 years. Why are house prices still going up there?
Yeah. I mean, I wish I had more insight into why Americans believe the things that they do.
So
you
you
know,
would say it's a belief story, not necessarily a fundamental story there.
I would say it's a belief story. Housing is a very unusual asset in that it represents a large share of all the wealth in the US, like all the asset value across all assets, and yet it's primarily individually owned and extremely non-diversified, right? So, even a few people, even one person offering, to buy a house from somebody else who is wrong about, how much this place is going to be underwater in 10 years, they are able to move the price of that asset, right? You don't see this in stock markets. One person being wrong about the value of Coca-Cola is not going to change the Coca-Cola price. And so, it really goes down to the fact that maybe this is speculative, that people who are buying these assets are just they just don't believe that the flow of housing services and the cash flow represented by this asset is going to be, what it would be under the IPCC median climate change scenario.
Yeah, that seems about right. Well, great. I think that's all the questions we have, so we might end it there.
Sure.
Thanks so much, Jeffrey. That was a really, really interesting presentation. Our next webinar is going to take place on April 7th. We'll have Joanna Harris from the University of Chicago, who will present her paper, Regulating ESG Disclosures. We're going to share a link to register for that in the chat. Thanks so much, everybody, for joining us, and we look forward to seeing you next time. Thanks again, Jeffrey.
All right. Thank you so much.